Welcome to all attendees at this session. I hope you are doing well. My name is Rayhan Tirto Nugroho from Institut Teknologi Bandung that will present our study entitled Source Rock and Oil Geochemistry in the North Seram Basin based on Surficial data. Before that, let me introduce Mr. Galih Hariyuna Yomandha, Mr. Majeed Hartono, and Mr. Joko Wahyudiono and Mr. Eddy Ariyono Subroto as the co-author of this paper. Let me begin my presentation. First, introduction. There are 128 sedimentary basins in Indonesia, with over 20 basins are generative basins. However, many generative basins are situated in western Indonesia. Recently, the basin in western part of Indonesia have become saturated with the exploration and exploitation that took place throughout the past century. On the other hand, one of the greatest potential that Indonesia has is the frontier basin located in the eastern side of Indonesia. One of the biggest reserves known to be located in the Banda Arc is the Seram Basin. The North Seram Basin itself is one of the other frontier basins that exist and is proven to have petroleum system. Therefore, this paper will study the presence of the source rock as the most important aspect of the petroleum system of the two formations in the North Seram Basin using geochemical data such as total organic carbon and pyrolysis data from 24 surficial samples. Biomarker characterization was also carried out from the unoiled sample derived from extraction on one rock sample, which was then analyzed using gas chromatography instrument and gas chromatography mass spectrometry. The crude oil sample was then correlated with the source rock based on the characteristic of the biomarker. North Seram Basin is situated between the Seram Trough and Banda Sea, which is part of the Banda Arc line that is formed due to the interaction of three large plates, which are Pacific Plate, Eurasian Plate, and Indo-Australian Plate. There are lots of tectonic episodes during the formation of the North Seram Basin that could be divided into three major events, which are rifting period, drifting period, and thrusting period. During the Paleozoic, the North Seram Basin was situated in the northwest part of Australian paleocontinent. In the early Triassic, the northwest part of the Australian margin undergoes intracratonic rifting. During the rifting initiation, some limestone and clastic rock were formed in the structural depression of the basin that commonly refer to Saku Formation. The rifting became more intensive due to the opening middle Tethys and transgression also occurred, so that conical formation was formed. As you can see in the figure 1, in this period, graben was formed. In the late Triassic until Middle Jurassic, there is a change in the positional system of the North Seram Basin into carbonate platform. In the southern highland of the basin, the Manusula Formation consists of oolitic limestone and skeletal limestone is formed. In the north central part of the basin, the Saman-Saman Formation is formed, which consists of dolomite, grail marl, and mudstone. In the late Jurassic, there was a depositional hiatus due to the decreasing seawater level and regional uplift, which we consider as a breakup event. This breakup event is represented by a colossal formation that overlap Manusula Formation unconformably. Following the breakup event, the tectonic activity becomes stable. It can be seen from the green layer, which is relatively the same thickness. And also, its setting turned to be a passive margin in the late early Cretaceous stage. Transgression also occurred, so that the depositional environment also changed from the outer shelf into bathyal environment, resulting on the deposition of Neve Formation. In the late Miocene, normal faults were formed during the rifting period were inverted into thrust fault due to the strong collision between Australian, Eurasian, and Pacific plates. In the northern part of the basin, the fourth belt began formed as the result of the evolution of structure set associated with the thrust fault. From the late Pliocene to early Pleistocene, the tectonic activity became more stable when it was compared to the late Miocene tectonic activity. The tectonic regime have been changed from compressional tectonic into strike slip. It can be seen from the floor structure in the figure 1. During the early Pleistocene, the Fuva Formation was formed. This formation overlaid the Wahai Formation that is deposited in the outer shelf environment on the late Pliocene. The research area of our study itself is situated on Seram Island, Maluku. The sample used in the study were 24 superficial rock samples, which consist of claystone, siltstone, shale, and mudstone. Oil chips sample also taken from the field to be analyzed. The methods used in this research are geochemical analysis, specifically pyrolysis and TOC analysis for superficial sample and biomarker analysis for oil sample. Biomarker analysis was carried out from the result of gas chromatography and gas chromatography mass spectrometry analysis. All the analyses are done in Lamigus laboratory. Moreover, biomarker data from the crude oil sample also used from the literature data. Before the source rock began to evaluate for the characteristic, contamination assessment was also carried out using a cross-plot of production index and Tmax with the value from Peters et al. This aims to determine whether there are contaminated samples, since our samples are taken from surveys. The existence of non-indigenous hydrocarbon sample could lead to erroneous in interpretation. As you can see in the figure 2, a cross-plot of PI and Tmax shows that 3 samples have been contaminated. Specifically, 2 samples from Kanika Formation and 1 sample from Saco Formation. Therefore, the 3 samples are discarded and not included in the further discussion. After we got the samples that not contaminated, we use TOC and S2 value for determining the quantity of organic matter. Our data shows TOC range from 0.5 to 3.73% that are classified as fair to excellent, and S2 range from 0.03 to 8.54 milligram hydrocarbon per gram rock that are classified as poor to good. So, the quantity of the organic matter from Kanika Formation range from poor to excellent. The different value between TOC and S2 value in Kanika Formation are the result in the different analytical methods of TOC and pyrolysis analysis. TOC represent all the organic carbon in sediment. Meanwhile, S2 represent the organic material that could produce hydrocarbon. After the quantity of organic matter has been determined, a cross-plot between TOC and S2 was used to gain information on the kerogen type. Based on the diagram, Kanika Formation is composed of type 3 and type 4 organic materials. The samples predominantly spread out on type 3 and type 4 kerogen, while a single sample is observed as a type 2 until type 3 kerogen. It is also reflected by the hydrogen index of the sample. It shows that the Kanika Formation is dominantly composed of type 3 organic matter. The occurrence of type 4 organic matter could be possible as the result of the over-mature condition of the source rock. Therefore, the maturity of organic matter should be assessed and discussed in the next section. The source rock maturity is determined by pyrolysis analysis result, which is the max value, since vitrinate reflectance was not conducted yet. The classification from Peters and Casa is used to determine the thermal maturity based on its Tmax value. A series of data which have an S2 value more than 0.2 milligram hydrocarbon per gram are chosen. This should be prevent error in the interpretation of Tmax on the resulting diagram. 7 samples are being discarded due to the low S2 value. The other samples show Tmax value range from 419 to 464 degrees Celsius, which indicates that the sample are immature to late mature. The immature condition of the source rock is possibly the result of the basin configuration and also the tectonic history of North Seram Basin. The early Cretaceous uplift and late Miocene roasting period possibly remove the burden of Kanike formation. This means that the data were being taken from an outcrop that might have been experiencing uplifting due to the tectonic activism, which result in derivation of thermal gradient on specific area. Therefore, the source rock did not have an appropriate maturity in certain area. After the source rock being evaluated for the characteristic, to correlate it with the chloride sample, the biomarker characterization was also carried out. The source rock, the source of organic matter, is interpreted from the normal alkane peaks resulting from gas chromatography analysis. In addition, heterogeneous aquatic ratio is also used to determine whether organic material input is relatively coming from the heterogeneous or aquatic materials. The chromatogram from oil sample shows the presence of two peaks. The peak is observed below the normal alkane C22, while the other peak was recorded above the normal alkane C22. This indicates that the source rock is composed of two organic matter input, which is algae and higher plant. The TIR value of the sample is 0.87, also suggests that the input of organic material is almost balanced from heterogeneous and aquatic materials. The isoprenoid ratio was also used in the study to identify the characteristic of the source rock that expelled the crude oil. Based on the crossplot between V10 per normal alkane C18 and pristane per normal alkane C17, our data shows the crude oil sample is derived from the source rock that is composed of mixed-type organic matter. Also, the data from Wahyudiono et al. And Price et al. Shows respectively that oil sample were derived from source rock that is composed of type 2 organic matter and spread out from type 2 and type 3 organic matter. However, the use of alkane biomarker and isoprenoid must be put in caution due these parameters are sensitive to secondary process in the form of thermal maturation and biodegradation. Peters et al. In 2005 stated that the role of oxygen compound in the depositional environment, which could be identified by the C29 per C30 Hopen ratio obtained from GCMS analysis. The C29 Hopen is dominating over the C30 Hopen, which indicates that the rock sample is applied to an oxic condition. Quantitatively, the very high ratio of 52.04 shows that the crude oil sample is derived from the source rock that is deposited in an oxic condition are typically occur in a characteristic marine shelf. Hence, it is thought to have been deposited in the marine environment. Stirring composition of MZ217 fragmentogram also could be used as an indicator of paleoecosystem. The information could be correlated afterward with the depositional environment. The indicator used in the ratio between C27, C28, and C29 stirring, based on the MZ217 fragmentogram, it shows that the peak of the C29 stirring is relatively higher compared to C27 and C28 stirring. Based on the ternary diagram from Huang and Mainshine, the plot between C27, C28, and C29 stirring shows that the source of organic matters of the samples comes from terrestrial environment. A set of oil seeps from Price et al. Also observed and shows that the source of organic matter were coming from estuarine. Therefore, we can conclude that the depositional environment of the source rock was occur in the transitional area. It is observed that existing oil sample may have been experienced biodegradation. However, it is still possible to use C27, C28, and C29 stirring ratio in the ternary diagram of Huang and Mainshine to determine the depositional environment. The interpretation should be valid due to the values proportion between the stirring composition will not change with the assumption that biodegradation will occur evenly in each component of crude oil sample. Based on the discussion above, our study shows that the Kanika Formation acts as a source rock with a wide range of organic richness from poor to excellent. Kanika Formation is mainly composed by type 3 and type 4 organic matter, so that Kanika Formation is a gas-prone source rock. The occurrence of type 4 organic matter is related to the maturity. The maturity of samples range from immature to late mature. The immature condition of the source rock is possibly the result of the basin configuration. The early Cretaceous uplift and late Miocene resting period possibly removed the burden of the Kanika Formation, so that the source rock did not have an appropriate maturity. Those characteristics are clarified with the crude oil sample data, which shows that crude oil sample is originated from the source rock composed by type 2, type 3, and mixed type organic matter, which are derived from the terrigenous and aquatic materials. The source rock of Kanika Formation is deposited in transitional environment. Hence, the deeper part of the Kanika Formation may have served an effective source rock, which not only acts as a minor source rock, but also possibly as a type 3 source rock. The authors also suggest further study which needed on Kanika Formation, such as basin modeling, for a better understanding on the source rock. Here are our reference of this paper. Before end, the authors would like to acknowledge the Pusat Survei Geologi Geological Agency, especially Mr. Joko Wahyudiono, for permitting us to use organic geochemical data from the North Seram Basin for this paper. Therefore, the paper could be presented in PIT-IAGI 2020. And thank you for your attention. We are open to any discussion about this paper. I hope you are always healthy, and thank you